Cool. Good morning. Lovely to be here. Yeah, I'm Tobias Kleanthous. I'm the director of Tencent's IGG production R&D team. And I'm joined here today with my colleague, Antonio Martini, principal machine learning researcher. And we're going to talk to you a little bit about our paper, Learning Robust and Scalable Motion Matching with Lipschitz Continuity and Sparse Mixture of Experts. So just to outlay what we'll be talking about today, we'll give a little bit of background and overview of the areas. We'll talk a little bit as well about the two kind of key parts of our paper, which is the robustness from the latent regularization that we've been working on, and the scalability that enables us to hit really fantastic performance numbers with this. And then we'll have some conclusions. And yes, after that, please do read the paper for more details. Okay. Cool. So just to set expectations around where we are in the games industry, at least for video game animation. We are at a point where there are ever-growing expectations from audiences and developers to further improve animation technology in games. And right now, we have many industry-adopted techniques which are fairly standard throughout games. So finite state machines, where we explicitly sequence our animations together. Animation blend trees, where we're usually selecting on parameters or parametric blending sequences together. And then in recent years, motion matching has had quite a big impact on the games industry at large. Motion matching solves a lot of the problems with explicit parameterization, although it's not without its own downsides as well. Alongside that, we've seen a lot with research techniques around motion graphs, motion fields, and more excitingly, in recent years, there's been a growing number of techniques coming about with neural networks. And that's something that we've been very interested in, and we're going to talk a little bit further about today. So just to go back on the motion matching. Motion matching has become a bit of a gold standard in what's referred to as AAA video games. And this solves a lot of the problems, like we were saying before, about explicit parameterization or sequencing. So typically, large amounts of data are organized in a database based on parameters such as joint positions or velocities on a character, and then goals that you want to achieve. So those might be things like future trajectory points or gameplay actions that are tied to timing or events. There's also been a big growth in synthesis around ML techniques as well, but they all have a bit of a problem with trade-offs in terms of how much they cost to execute in different areas. So the typical trade-offs that we're ending up making is CPU cost in terms of how expensive is it for these actions to be performed on target video game hardware like video games consoles or mobile devices. Memory, which is a significant issue with motion matching, whereby often the database, as you add more detail to it, the memory cost scales pretty linearly with that. And then quality, because often we make a trade-off then in terms of if we're going to reduce memory usage, we more heavily compress data. So we've seen, with a lot of the neural network-based solutions that they're converging towards reducing the memory cost and solving the quality, but not solving the CPU performance issues. And this is always a contentious area when you're trying to ship a video game and improve the standards, because every single system is vying for those resources. So currently, you can't have them all, right? So our goals are to effectively look at it and go, okay, well, we'd like to solve all three. We'd like to take the CPU performance and significantly improve upon this. We'd like to take the qualitative and memory size reductions that come from neural network synthesis and apply these as well. And we want to make sure that these were practical and could be applied to shippable video games in the near future. So for our paper, we have based a lot of it on learned motion matching, where we've preserved the three-model architecture that was solved in that paper, which replicates motion matching by splitting it into three parts. So there's a autoencoder, which encodes poses into a latent and then can be decoded at runtime, giving a compressed representation. There's a projector model, which replaces a spatial search from motion matching, which is used to find fragments of animation to put back together. There's also what's been called in the paper a stepper, which is effectively replicating the idea of seeking forward in an animation and predicting what's going to come next. Now, in learned motion matching, the quality and the memory performance were all really effectively very well solved. Now, in our solution, we are basing it again on motion matching. So we use animation-derived features, which are, in this case, explicitly set up. So we are looking at, in the case of the video that we see on screen, we're looking at like foot positions, hip velocity, feet velocity, and as well as that, we're looking at some historical information about trajectory and the future targets that we want to take. Alongside that, we've also implemented for all of our pipelines that we built upon this usage of deep phase that was published at SIGGRAPH last year, whereby we automatically derive phases using the periodic phase autoencoder. Okay, so a bit of background there. So I'll go into the first section where I wanted to talk about the robustness. So by robustness, we were talking about the latent regularization and the impact that this has. So when we started out, we took a view of what was out there for latent regularization for animation papers in the past. And I've highlighted two examples here. So learned motion matching had L1, L2 losses for compactness and proximity losses to address coherence of the frames, trying to preserve keeping nearby frames of animation data together. Positives there, it's a really tight fit for representation, but there's a low utilization of the dimensionality out of it. And in the paper, there's a lot of discussion around this idea of drifting outside of the valid manifold. So there's this autoregressive stepper model that predicts the future, but it can fall off the manifold quite easily. And this is where we see some issues with the robustness of representation. Alongside that, not so long ago, there's motion VAEs. So this is a variational autoencoder. In this case, it was the latents then guided over a Gaussian distribution. So big pros there. The control of the latent distribution is actually a bit more robust. But the cons that we've seen observed with that, there's a tendency to see over-smoothing, and how you tune the size of the latent can also significantly affect the results. Now, also, it has to be said, the training data distribution is probably not going to be Gaussian either. So for our case, we're trying to mimic what motion matching does. So we want to have this case where the data's representation in the latent manifold does really represent the author's intent, the artist's intent when they create the animations. So nearby frames of animation should be nearby in that space. But we want to make sure it's robust and, that there is a valid kind of solution within that doesn't necessarily end up with lots of gaps of nothingness in the manifold. So the motivation, find smooth regularization function. And we wanted to see if we could enforce predictable gradients in that latent manifold. We wanted to reduce some assumptions about the distribution of the data. Like I said just there, we're not assuming it's going to be Gaussian. And making sure there's that clear relationship. So we fell upon Lipschitz continuity. Now, the idea of a function being Lipschitz continuous is expressed in this little diagram here. So if we take two data points in a set, x and y, in the original space, the distance between x and y multiplied by some constant should be greater than or equal to the distance of x and y with that function applied. So what that effectively is meaning is that we're looking at minimizing that gradient overall. The idea then being that any point that's put into that latent space, or any point that's actually acted upon by the encoder in our case, should be nearby to any other data that's nearby in the source data. So this technique came about as we observed it applied to SDFs, whereby they were shown in a paper in SIGGRAPH last year, where you could use them for a linear interpolation in the latent coding. So for us, this complements the existing regularization, and it can learn near linear relationships between the samples like we wanted to see, but it also gives us that intuitive mapping that we're interested in. So if I have part of a run cycle of a character, two frames in that space that are very close together in sort of intuitive posing should be similarly there in the latent. So just to give you an idea of how we actually implement it, In our case, we implement these Lipschitz layers inside the encoder, as in the paper mentioned above there. There's a learnable constant that's applied per layer. What this is used for is for normalizing the weights of the matrix in any given layer of the neural network. So the idea then overall with this is that for any data that we put in, there should be a minor change if there is a minor change to begin with. So for our case, we develop a scale where, as you can see in the equation above, we use soft plus on the C. We take the sum of the rows of the matrices, and then we multiply the base matrix by that to give us then a normal weight that we can then multiply the input and add a bias as standard. What's great then is also that can then be cached off for runtime performance. So we don't need to keep the constant about, we can just store off the weights. And then when we're trying to minimize the loss, we're looking at a cumulative product loss. So we take each layer sequentially, multiply it by the prior after applying soft plus. With this, when you tend to put this into your network and into your training, you end up with pretty large losses on it. So it can be a bit of a distraction as to knowing how it's going to perform. And there's some fine tuning of it. But we find as well, there's an alpha that's applied onto it. After a certain amount of it, a certain level, it doesn't make much of a difference to what comes out of it. So I just want to demonstrate some basic projections of that space, right? So at the top, you can see the 3D projection of our latent space after Lipschitz regularization. And at the bottom, you can see the same data with the learned projection from learned motion matching. Now, the intuition with this is that we don't end up with these issues of stratifying the space. So we don't end up with gulfs whereby large amounts of the manifold aren't actually used and undefined results are inside there. We want to actually make sure it's very dense and that really the relationships are actually preserved, like I said a few times now, with what the original animation data looked like. Oh, there we go. Okay. So, after applying that, the latent manifold is actually relatively well bounded, which gives us a huge benefit in that we can now blend within that space as well. So it's a smooth and well-defined representation. The bounds are valid outside of it, not necessarily well-defined. But it gives us this ability to then, at any point, actually linearly blend as we would do in the original animation space. Now, the reason that that's really useful for us is that it also means that the issue that we see in learned motion matching, the notion of like drifting out of the valid space, isn't as significant to begin with, because within the bounded latent, pretty much all of it is well-defined and acts similarly to a linear blend of the source animation data. So in this case, you can see here, we're taking some samples from ground truth from the data set that we learned on here. And then we're actually blending the latent for the result in the middle. And across all of that, we get a coherent result on the in-betweens, but we also avoid some of the more gnarly issues like leg crossing coming up as well. So from that, then, because we've got a really well-formed space there, we can then improve the prediction results that we see out of the stepper model. So we implement the stepper as in learned motion matching, which is an autoregressive model trained to effectively predict the next frame on the latent and motion matching vector encodings. So we take a very, very simple approach to this. Basically, we induce some noise by applying the standard deviation of each of those two vectors and randomizing them with some Gaussian noise on top and a small scale there. In our case, the lambda scale there is about 0.15. So we train with our first sample on the autoregressive model to take that in, and then we just carry on predicting for some 30 or so frames into the future. Now, the results there for us are then being pretty good in terms of robustness, because we can now predict over a longer time frame without searching for a new sample, without drifting off the manifold sort of so badly. So in the case of the video that I've got on screen at the moment, we're injecting noise on both of the right and left-hand side and predicting some number of frames into the future. So on the left-hand side, we're seeing the results of training as in learned motion matching paper, and on the right-hand side, we're seeing with our method. And as you can see, we're coloring it as well to show just error over time that's introduced. Now, as we go longer and longer into the future with it, we see that we get error on both sides, but the failure model is pretty graceful. So rather than just collapsing into an undefined pose, we always have a coherent result come out of it. In practice, what this means then is that we can limit the time that we do predictions when we apply this in a runtime system, but we can be fairly confident that we won't produce anything where we collapse a result and need some sort of level of checking on that afterwards. Combined then with the regularity of the space, meaning we can blend in it, this then gives us this ability to continuously treat these animations, the animations in the latent space, as we would do with motion matching just played on normal compressed animation data. So, for instance, if you're familiar with things like, there's techniques like inertialization, where you can cut off an animation and then immediately blend with some physical properties into the next one, we can actually continue to play them contiguously, blend them together before decoding and getting the final pose. Okay, cool. And with that, I'll hand over to my colleague, Antonio.
Hello, everyone. So the original learned motion matching paper relied on dense neural networks for all components, for both the decoder, stepper, and projector. So the problem with dense architectures is that essentially are these stacked dense layers. The problem is, as you get more training data, you need a bigger network. So as you increase the network weight, there is a quadratic explosion of terms, because adjacent dense layer, when they are stacked, they scale quadratically their connections scale quadratically as a function of the network width. So this is highly undesirable and scales very badly. So in order to find a solution to this problem, what we wanted was high accuracy and high scalability. And we took inspiration from recent advances on what is happening for training and deploying large language models. Usually there are billions of parameters there, and these models need to run fast. And that's what we tried, and actually works very well. So our solution is to use sparse mixture of experts. So essentially, this is a drop-in replacement architecture for stacked dense layers. So if we focus on the picture on the right side here, we replace the big network with a small array of smaller feed-forward networks. Here we can see 5 of them. In reality, I think we use between 64 and 128. So we can see now how this works exactly. So if we start from the bottom, we have got the input X, which goes into a gating layer. A gating layer is simply a linear layer with a softmax activation function, which generates the expert's activation probability. Then we dispatch the input X only to the 2 experts with the highest activation probability. Then the 2 experts will compute their own outputs, which is weighted by their respective normalized probability of activation, which is essentially, you can see that in the broken arrows. Then we sum the outputs to obtain the output Y. So we can see as we get more data, we can have more experts, but the complexity is constant in the sense that only 2 experts are active at any given time. So different inputs will activate different experts. So one problem when training these architectures is that certain experts could receive more data than others. So there is a risk of having under-trained experts, or maybe experts that don't receive any data at all. So in order to ensure that all the experts receive approximately the same amount of data during training, so that we exploit the architecture in full, we employ a load balancing loss. So the purpose of the loading balancing loss is to assure the experts receive training data in roughly an equal amount. So we have experimented with different losses here. This is the first one coming from the switch transformer paper from Google. And then we have a second loss which works better. So we go in order now. So this first loss here consists in two components. We got two vectors, f and p, and their dot product. F is simply the fraction of batch entries dispatched to each single expert. And P is simply a vector of the unconditional probability of experts activation. We just estimated by averaging over all the activations. So this loss works in practice, but is not satisfactory. There is no formal derivation. And as we will see, there are a few problems with it. So the claim of the original paper is this loss will reach a minimum when at 1/n, where n is the number of experts, and that corresponds to when the experts are approximately balanced. And that is when both f and p, all their entries are equal to 1/n. However, if we start plugging values by hand, we can easily create examples where the loss is smaller than the stated minimum, and even with non-uniform experts utilization. Yeah, we're going to quick example, 2 experts, 3 inputs. Each row is the softmax activation for each input. We see when we do all the calculations on the bottom right, we got the cost is 0.447, and the utilization is not uniform. So clearly this loss is a bit problematic. So in the end, we do something else. This worked for us, so I'm not saying it's bad, but there is better than that. So what we do, we simply minimize we don't use that loss anymore. Currently, we use this other loss here, which is simply minimizing the KL divergence between the unconditional probability of the expert's activation and a uniform distribution over the experts. It's a very simple formula. P is the same as before, is the unconditional probability of the experts' activations. So before going to the conclusion, we utilize this sparse mixture of experts architecture can be seen as a single layer, which can be incorporated into larger architectures. We are using it for animation, but clearly it could be used in other domains. Now over to Tobias for the conclusions.
Thank you. Cool. Okay, so I'll try and whip through these quite quickly for you as well. So the conclusions with this. Okay, so the big motivation with it is basically, like I said earlier, I'm a recovering game developer myself. And so we're trying to address the issues around getting the performance, the memory, and the quality there that we want to see to get these methods tractable for game developers to start integrating into their games. And so if you see in the numbers in our paper, you can see that our performance metrics as a result of these different techniques are well below what we've seen in some great papers like learned motion matching. So when we compare learned motion matching in total, that's a system that takes a surprising chunk of a millisecond. And typically in a video game, if you're working on a high-end video game across consoles, 1 or 2 milliseconds of time per frame for animation for everybody, even if this is a big open world with a city full of people, is a lot of time. So 0.2 from learned motion matching is large, despite the memory savings that are there. In our method, as you see here in the table extracted from the paper, we're actually well below that. In total, for executing on a single character, and this is a full detailed rig, including fingers, helper bones that you typically see for things like IK targets, and everything really largely, apart from the face, we come in at just above 25 microseconds. And then alongside that, our memory reduction is quite substantial as well, because we come in at about 3/4 of what learned motion matching has, which was already great. So in total, then when we compare that to the results of a base motion matching system and learned motion matching, in both cases, we come in much lower. And actually, if you look at the standard of actually just decompressing an animation in Epic's Unreal Engine right now, using a library called ACL, just decompressing a frame of animation before you can do anything extra with it, actually largely comes in at a similar cost to what our entire system does for all the queries running up to something on screen. So just to summarize, Lipschitz continuity is a better latent representation for animation data, preserves those relationships between animation frames that we want to see. We've also seen it unlock some new blending capabilities. So we are seeing other applications for what we've learned here as well. There are some limitations in the paper because it's based on what learn motion matching did. So we don't use Lipschitz in the decoder because the concatenated motion matching vector that comes in is not guaranteed to be Lipschitz continuous. And consequently, if we do use them, actually get poor results from the decoder. So we don't do that for now, but we are looking at this. Sparse mixture of experts. This is a huge gain for us, as we've seen. Hugely efficient, like Antonio said. The experts themselves, as you'll see in the paper, are actually incredibly tiny. And early on, we were very surprised the level of expressibility in animation data we could get with such small kind of minor MLPs within the larger network. We do actually train this on huge batches of data to get a good distribution. The layers can actually be employed as components of larger architectures, like Antonio said, but we use it liberally across this entire system that we're talking about today. But we do think the benefits very likely do expand like well beyond just animation data as well. So it's a really interesting one to explore further. And we also know that the experts can actually scale to increased data sets without increasing the actual computational cost. So you pay a memory overhead increase for significantly more data, but the actual execution can stay the same. However, just as it is now, most of the kind of runtimes that are used in game engines for actually running any neural networks, although this might have changed since we typed this out, are usually based off an NX runtime, which cannot correctly conditionally execute the experts and so loses some of the gains. So in our case, our numbers come from our in-house model to C++ compiler. So just to finally summarize it all, and I think I may have gone a little bit longer than I should have done, but we're showing that neural network-based animation synthesis is now practical for runtime use cases without compromising on any of those key areas. So CPU, memory, and quality, none of them need to be compromised, and we don't have to vie for additional resources like GPU for execution either. The other great thing as well is this means then they're all executed on CPU. We have multi-threading capabilities on modern hardware. So those low numbers, in practicality, they don't mean that that's going to scale up, linearly for how much time you're going to take per frame for the number of characters. The only limitation that we're still stuck with is the training times of neural network approaches still remain a limiting factor. There is still that iteration time. So in our case, where we've implemented this into a system, we still provide a motion matching implementation for people to be able to quickly edit data. And that is us.
Thank you very much.